All right. So I think if you're in computer science, you should have this basic understanding, right? You should know what problems can be done in constant time, right? So what constant and what? It's your data structure is of size n, and it takes me order n time to just look at it all, right? But if I want to push somebody on the stack of the queue or pop somebody off on the stack of the queue, I want I want it to be constant. I don't want to look at the whole thing, right? Everybody get that? And then logs are really, really small. They're almost constant, but they do grow, and you can do binary search, right? As I said, if you have to look at all the data a constant number of times, then it's linear. N log n is sorting, quadratics, polynomials, exponentials, right? So exponentials grow really fast. I mean, really fast. So as a general rule, you never want to run an exponential time algorithm, right? Everybody good? So these operations are all constant time. This is constant, right? It doesn't look very constant, but it's bounded by a constant, right? Everybody buy this? There exists a constant so that as n gets big, it may wiggle around, but it doesn't go above the constant, right? So I think this is an important concept. If I give you, I mean, there's so many problems of this nature, right? Well, in this one, I give you a circuit, and if I give you the assignment to the circuit, then evaluating it, you can do that in order n time, right? Whereas what's n then? Well, it's the size of everything. It's the number of bits you have here. It's the number of gates you have here. You got to look at it all. You got to look at your entire input, both the input and the circuit, to figure out what the output is, right? But order n, that's fast, right, in this world. Now, this guy here, if I give you the circuit but not the assignment, and I have to search over all possible assignments, that's bad, right? Because if n is the number of bits on the input, then there are 2 to the n assignments, right? And if you want to know why did things like AI fail through the 70s and 80s and 90s, because the only algorithms they knew were trying to find exact answers on problems that they didn't know how to do except for brute force exponential time, right? Now machine learning doesn't always give you the answer. It's very fuzzy, but it does sort of well, right?
Hello, Professor.
All right, so this is one of my pet topics, is the knowing the difference between these running times. So if I give you a value capital N, right? I give you some value capital N, and I loop I equals 1 to n. Is that a fast algorithm or a slow algorithm? You remember, this is where I have a little something, I'm particular about something and you guys never get it. This is one of the examples. All right? So this clearly looks stupid, right? But suppose I have 2 values and I'm multiplying them. Well, the algorithm on the right is basically this. You're counting up to y, right? And I can give you y. How much time does it take me to give it to you is the number of digits. right? And the value either is 2 to the n or 10 to the n, but depending on your base, the value's big, right? So if the size of this input here is log n, is little n is capital of big N, right? Little n little n is a log of big N, right? So if the time is n, then it's 2 to the little n, right? So you all know that you don't want to do that kindergarten algorithm when the numbers are big, right? And the reason, because it's exponential in the number of digits. Well, the high school one, if you have n digits, is n squared, right? Everybody getting that? So the size is the number of digits, right? And time complexity is how much time does it take me to give you all the digits of the input versus your running time, right? I can give you this fast, but you don't want to count to it, right? This is not on the test, but big O is less than or equal to, omega is greater or equal to, theta is